now. Okay, so hello, and here we will have the last two lectures in one block by Dmitry Noshchenko.
Yes, thank you very much, Piotr. So just to recap, we have ended up last time discussing Quivers equivalences. So that is, we discussed how the two Quivers, which have the same Quivers generating functions, are related. And in particular, we have discussed one source of such equivalences, which comes from unlinking operation. And this unlinking operation effectively removes the pairs of nodes for a given quiver and adds additional node and some connections. And those two quivers are equivalent. So they have the same generating functions after proper identification of generating parameters. And most important outcome of the previous discussion was that by studying different algebraic relations satisfied by unlinking, we have ended up with definition of a permutohedra graph. Or actually, we have studied the very simple example. So a permutohedron coming from unlinking, which only consisted a pair of equivalent quivers. And these two equivalent quivers are related by permutation. So in fact, these two quivers were labeled by permutation and also could be unlinked once to lead to the same quiver. So today the plan is to move to knot homologies and to discuss how this permutohedra appear for knot homologies first, and then try to relate to this more like formal algebraic picture from unlinking. So let me perhaps clear the board now and just start. Yes, so let's start with knot Quivers correspondence. Yes, just to quick recap. So this correspondence states, so it could be probably formulated at least on two levels. So the first is more like a computational level, which effectively relates. So on one side we have some nodes. So let's just draw, for example, like a trefoil node. And on the other side, it relates some symmetric quiver. In particular, I can already draw like the answer to the trefoil node, which has three nodes with 0, 2, and 3 loops accordingly. And there are some connections between them. So namely, there is a pair of arrows here, there is a pair of arrows here, and there are two pairs of arrows like this way. And yes, so we have here node. Or more generally, this could be a link as well. In principle, in today's lecture, we only focus on nodes up to 5 crossings, but we can also consider various links. And here we have symmetric quiver. And how this correspondence goes, that it relates, so on one side we have a generating function. Of conflict PT polynomials. In some specific representations. So we take a representation So I will explain in a moment in more detail. So the representation would be symmetrical ones, and essentially this would be polynomials which are labeled by Young diagram, which is just a single row of boxes and by length R. And on the larger side, we have symmetric Quiver, and we of course have the Quiver generating series, which we have studied before. So this object, for example, here would depend on three generating parameters, and the statement of this correspondence is that so we can identify these two guys. So when one takes now this x1, x2, x3, so we pack them into a vector. For example, we can write, yeah, so here are generally some coefficients of these forms. There's some a, q, t times x. Here we have like a1, q1, up to a, n, qn. So in other words, there's some monomial change of variables such that after a proper identification, so this index is CMM, so we have the size of the quiver times x. So some monomial in A, Q, T times just a single variable x. So this is one level, and so more conjectural level. So this is in fact a theorem that for a large class of nodes, one can establish such a correspondence, namely, so for a node, there exists a quiver, which is not unique in general. So in fact, there are large classes of equivalent quivers corresponding to the same node, but one can establish the equality between quiver generating series and generating series of Hom-Floyd-Petit polynomials. And so the more conjectural level is more like a, so what happens if you lift these two homologies, and in fact, Hom-Floyd-Petit polynomials could be also considered as Poincare polynomials for Hom-Floyd-Petit homologies, and the statement would be so what happens if you have here we have Hom-Floyd-Petit homology, and on the quiver side we might have some algebra, but there are several candidates for this algebra, and so in particular in this lectures I will not cover the details, but particularly in June there would be lectures by Vladimir, and he would cover some relations, quadratic algebras, and one candidate would be some algebra denoted capital A of Q, whose generators are in one-to-one correspondence with the nodes of the quiver here. And okay, so this homological relation is more conjectural, and we don't know much about it. So in these lectures, let's just focus like on this more computational level of identification of generating series. Yeah, so just a very quick recap about the node homologies. So essentially, yeah, so we may start with Hom-Floyd-Petit polynomials again. So if one draws the usual Hom-Floyd-Petit, it is a polynomial in two variables, so A and Q. And well, this could be defined using scan relation. For example, Yeah, and maybe I can just briefly draw this relation. So this is the very usual stuff. So one can draw the planar diagram and then define this polynomial by the following relation. So where we flip crossings in a diagram and we can resolve them in a certain way. So this goes to skew inverse. And initial condition, let's take that we have unknowns, so this is equals to 1. So this is called reduced uncolored Hom flippity. And here we have some node k. And if one speaks about colors, so then, okay, so one source to define colored polynomials. So this would also depend on some color, which would be some integer number, non-negative integer. And yeah, so these polynomials could be defined from Chern-Simons, as Rama showed very nicely in the previous lecture. So this will be Chern-Simons with gauge group UN. And in particular, considering representations which are symmetrical ones, so labeled by Young diagrams, so r-dimensional representations of UN, and then considering expectation values of Wilson loops, and Chern-Simons computes effectively these polynomials. And from our perspective, it's also important to remark. Okay, so of course, when we have just one box, so this is the usual polynomial. And if you have several number of boxes, yes, for example, if you have R here, okay. See this notation, I just write R as an index. In fact, I can just write PR. So this is R colored polynomial, and then there is some identifications. In fact, it's almost the same as taking the colored ones and just exponentiating to power R. And this does not hold for every node, but so this is what is called the exponential growth property. So this only calls for a class of nodes, and in this talk, in fact, we would focus only on these nodes which satisfy this property. And by this symbol here, we really mean the bijection between generators. So if one considers, okay, so I have, so I speak about generators, but I have not yet introduced these homological gradings. In fact, I do have to say first that, so since we want a homology, so we want to introduce a third parameter here. So we want also to add parameter t, which would encode homological grading. But it's not possible just to upgrade like in a naive way this kind of relation. And yeah, so introduce this t, in fact, it's a little bit tricky. But it could be done like using some axioms. And then, yeah, so then, in fact, you would also have t here and t here. And then I can say that so then I can say that this upgraded polynomial, which has 3 variables, so then this just the dimension, so there will be some Q. I, QI, QJ, TK times dimension of some homology groups. I, JK, which also labeled by the symmetric representations, or simply are. Yeah, so to define these homology groups, it's also a little bit out of scope, or I see another question in the chat. Yeah, so Ramadevi noted that exponential growth when Q equals to 1. Yeah, I think, well, yeah, I think so. Although, yeah, I think so. So perhaps indeed here I should have written Q. Yeah, so this formula, if you write correctly, so I have this here, this new parameter T. Yeah, so this formula. Yeah, but I didn't say that. So correct me if I'm wrong. So I didn't say that this is an exact equality here. But if you set Q equals to 1, so then in fact this equivalence is an equality. So if Q goes to 1, so then we have an exact equality between this guy. A QT is just equal to, yeah, so yeah, A1 T equals to this guy here. So if Q is not equal to 1, we still have this bijection between the monomials. So this is very important, in fact. So we have a bunch of monomials here, a bunch of monomials here, and there's a bijection between monomials here and there. But this is not, of course, they are not the same. So the polynomials, they are different, of course. But this bijection, so I will explain later in examples how this works and how this gives rise to a permutohedra. Yeah, so so today it's a little bit loose presentation. So because I do not define all these objects, I do not define not homologies in particular, but just believe me that there are such groups, and well, in principle, these are well defined mathematically. Well, at least in fundamental representation, and there are some constructions and how to use some spectral sequences to lift it to more general representations. But this is of course a little bit different from what we want to do. Yeah, so what we can do, in fact, that, okay, so now we have these polynomials and we can pack them as a generating function depending on node k. So here also depends on node k. And yes, now generating function. So now it depends on 4 variables, also generating parameter x, and this simply encodes all colored Poincare polynomials. So this would be PR of k and k, q, t. So we also can normalize with this Poincare symbol. And so now, given that, I think we're just ready to dive into examples. And yeah, so for the rest, of the talk. I will just consider all nodes up to 5 crossings and see which structures you can detect by using the knowledge that we gained so far. So let's just do these examples. So the first example would be trefoil oil. So 3-1. So there are two versions in principle, right hand and left hand. Maybe I can even draw them. So this is 3-1 left hand, and the right hand will be just slightly different. So this is like the mirror image. And these are not equivalent. And so just let's take this 3-1 left hand and write the Homology PT generating series. So for this guy, you would have AQTX. So this would be a double sum. So the first parameter would be R from 0 to infinity. So I'll just write it explicitly: X to power R, A to R, Q. And then the sum from K from 0 to R. So here goes Q binomial, RK times Q 2K plus 1. T to the power 2K times A minus A square Q minus square T Q square K. So where this guy RK just some ratio of epoch hammers. So this is Q. Now crazy. This is all squares. So we put Q square everywhere. So this would be R divided by K times Q square R minus K. So we have that, and in principle, so let's write the first color, the first Homology PT polynomial, AQT. So maybe so perhaps let me just first write this guy, and then I will add this T parameter here. So without T, this is just minus A4 plus A square divided by Q square plus A square Q square. So now, in order to, in principle, one could essentially put this by hand, and to do so, one can draw a homological diagram. So let's take all these three monomials and to put them on a grid. So one axis would be Q, so another would be A, and here we have we have 2, 4, minus 2, 0, and 2. So this is the result, and just to put T, one So the answer would be as follows. So t degree here would be 0, 3, and 2. And up to an overall factor, this could be deduced by looking at the relations between these monomials here. So since we have one monomial and like line in this cell and another monomial line like northeast from this guy, so then the t degree would be t degree here plus 3. So we have shift by 3, and here, like in the opposite way, we have shift by 1. So 2 goes to 2 plus 1, so this is 3. But this is, of course, up to an overall factor, and this is just fix it like that. So yes, here we have, now I can erase this minus sign, and I can put here t cube. So here I put t power 0, and here I put t square. And actually I probably put like minus t here. No, I don't. I'll just leave it like that. And when t goes to -1, one recovers just the usual conflict t polynomial, which you can compute also from the scaling relation. All right, so we have this homological diagram, and now, because I wanted to say about permutahedra, but in this diagram, in fact, there are no permutahedra, and yeah, to see that, perhaps it's useful to draw the second color diagram. So let's draw S2 color diagram. So as before, we had on one axis we had A, so another would be Q, and now yeah, now we have here we have 4, 6, and 8. Here we have 4, -4, 2, 0, 2, 4. It's a bit bigger. Need to prolong it a bit. So 4, 6, and 8. So in the moment you will see is what I meant by bijection. So when we have this exponential growth property, we do not have an exact equality between this uncolored one to power r, but there is some bijection between the two. Yes, so now the first thing I can draw the images of these 3 generators, which are mapped on this diagram. So the images of these 3 guys would be here, yes, so one here and one here. And now I can already start by decorating. So my goal is to decorate all the generators. So just recall that these dots, they correspond to generators of the homology. So these are just some abelian groups that you can compute in principle for a node. And put this decoration, maybe let's use another color. So here we have, this is x1, and let's say that this is x2 and this is x3. This is particular ordering that we have chosen in correspondence with the quiver that we had. So the quiver, just quickly draw it again. So has 3 nodes. Here we have x1. So the homological degree is 0, and we have 0 loops here indeed. So 0 loops. So here we have 3 loops, and here we have 2 loops. And yeah, so here we have x2, and here we have x3. And similarly, in the second color, one can also draw these decorations. Now we have x1 square here. So here we have x3 square, and on the bottom we have x2 square. But now the question is, so since we have S2 color, and so our goal is somehow to put these decorations xi, xj. So we need to put all these monomials, and we need to decorate them properly. And here there is a unique way to do that, and so the way it's done is just like you draw a straight line from xi, xj, and then you put in the middle. So let me draw it straight as I can, and right. So and then you see that there are 2 boxes which are just right in the middle between these 2 generators, and you put xi, xj into these boxes. So here would be the 2 boxes which are occupied yeah, and in fact they encode. So I would use maybe I use different color for them. So let's use the red color, and this would be x1, x3 here. So meaning that x1, x3 both correspond to this generator and to this generator. So similarly here, I just draw the straight line, and I see that there are 2 boxes here. So I put the pair of generator. Sorry, I need 3 different colors. So draw them red color. Right, so we put them here and say, so this is x2, x3, and similarly here, takes this pair, and this would be x1, x2. All right, so so the reason that we did not put x1, x2 in fact here is because again, so there are some extra axioms that this S2 color diagram must satisfy, and these axioms, they're dictated by the structure of the color differentials. And in fact, there is a statement, there is an axiom that says that you must have a differential like acting vertically, and it must so it must connect this pair of nodes. So otherwise, if you shift it, then this axiom is violated. So likewise here, there is a differential going this way, and there are also some differentials like acting in these directions, but for us it's not that really important now. So what is important for us is that we have a unique way to assign the labels xi, xj. So there is a unique way. To put labels xi, xj onto S2 diagram. And this unique way says that effectively we have only one quiver for trefoil, and this quiver is given by this guy, but we also, of course, have to put arrows connecting here. And to compute these arrows, this is still not entirely clear, like what is the meaning of these arrows, but at least one can say that if one has a pair of generators, for example, 0 and 2, okay, so 0, 2 is not entirely obvious, but those generators, which are again related by this configuration of boxes, so for example, 0 and 3, so in fact, there is a differential which acts from 3 to 0 and from 3 to 2. So there are two differentials. Here in these differentials, they shift the homological degrees. And according to this rule, so the number of arrows would be equal yes, so would be equal, but up to some shift to the degree of this differential. Yes, so can I say exactly? Yes, maybe I need to clarify that because otherwise it's a little bit. So what do I mean by that? So is that, again, so let's just write adjacency matrix of this Quiver. So now let's say we have a pair of generators, so 0 and 3. Let's take 0 and let's take 3. So we need somehow to know what is the value of Cij here. So y is 1 here, and y between 2 and 3, so I have 2 here. So this could be explained, again, based on the shift of the homological degrees here. So namely, maybe I can draw it all the way here. So if you have a diagram, so if there are two generators which are related by this this type of arrow, so by meaning that there is one generator and q degree is shifted by +2 here, and if you have going up a degree shifted +2, and then accordingly t degree shifted +3. So then we say that this pair of generators, so the degree of yeah, so if here we have CII, CJJ, so CIJ in this case is CII just CI +1. And likewise, yes, so if you had 0, so then the connection is 1. And likewise, if you have in the opposite way, so if you have a pair of generators related in this way, so then you have CII J. So yes, so in this case, CII would be CIJ, sorry, so CII plus 0. But otherwise, it's a little bit hard to say like about these arrows, for example, where a priori there is no differential connecting 0 and 2. Yeah, so it does require some extra work to determine these arrows. Yeah, so what's next? Yeah, so I said that there is no pentahedron here since there is a unique way of such assignment. And in fact, one can also see that I can draw this here. So again, the homological diagram was just a triple of nodes. And in principle, in order to have permutohedron, we must have at least 4 nodes. So if you add the fourth nodes, then what is possible is that we can have somehow this quadruple of generators. So we have I, J, K, and L. So then we might have a situation where Cij somehow exchanged with CKL, and this would give rise to some different quivers. So we have some quiver which correspond, for example, so permutation 1, 2, and the second quiver would correspond to permutation 2, 1. So corresponding to different, so Ij KL, for example, here, and if you permute them KL Ij. So this is what exactly happens for figure 8 node. And yeah, perhaps I'll show you figure 8 maybe after the break. So maybe any questions so far? All right, no questions. Yeah, but maybe a question to Piotr. So shall we make a little break now?
Yeah, it is up to you. So if you want, we can make a short break. I can hold recording. Do you want 5 minutes or how much time?
Yeah, 5 minutes is fine.
Okay, so it is 1:44, almost 45. So let's meet at 1:50.
Mm-hmm.
Okay. Okay, so we are back after the break, and Dima will continue with the last, the fifth lecture of the series.
All right. Yeah, let's now study the figure 8 node and see how this non-trivial permutohedron arise. So let me go way up here. So I will erase on the board. Yes, so we have for one node. Yes, I will just draw it as well. Yeah, so yeah, so for fun nodes, there are in fact two equivalent quivers. So let me first we draw these quivers. So they have been found some time ago. So the first one is the following one. So now it's a little bit different because it has also negative entries, so both positive and negative. But for us, it's all fine. So we still, formally speak, it is about a quiver, but we really mean this generating function. So we have 0 here, -2, -1, -1, 0 here. -1. So this is the first quiver, and the second quiver would be different by transposition of these two elements. So the quiver C2 would be virtually the same, but apart from this transposition. So now these two elements are transposed. So we have here we have -1, and here we have 0, and all the rest is just the same. So now why these two elements? So first of all, yeah, maybe just doing this step by step. So if you write the uncolored polynomial, so then it equals to 1 plus 2t minus 1 plus a squared t squared. Yes, now let's draw the homological diagram. Now it has 5 generators. So I'll draw also the homological degrees. Here would be 0, 2, -2, -1 and 1. So we are especially interested in this quadruple. So this quadruple would be connected by the differentials that we had before. And yes, so now you can see that the position where this redundancy appears, this 0, -1 goes to -1 and 0, it's essentially relate. So one generator is -2 connected to 2, and the second is -1 connected to 1. So you see that -2 to 2 and -1 to 1. So this is exactly this the so-called homological diamond. So we call this structure homological diamond. And in fact, every such diamond would give rise to a certain permutation. But so the question is now, can we see it more explicitly? Like, what is the meaning of this permutation level of homology? So for this, let me draw again. Yes, there are many drawings to make. So now let's draw a S2 diagram. And S2 diagram is built up similarly as for the case for 3.1, but it would be, of course, bigger now. So let's see. Yes, on the vertical, we now have from -4 to 4, so -4, -2, 0, 2, and 4. Yeah, and here we have the same as we had. Oh, okay, not entirely the same, because run from -6 to 6. Yeah, so now we can start drawing generators inside these boxes. So just to keep in mind that there might be several generators occupying the same box, which is totally fine. It happens almost all the time. But still, because of the exponential growth property, we have one-to-one correspondence between squared generators here and generators in S2 color diagram. So now we can, so first thing that we can do is we can try to plot the image of this diagram in this second color. So we can try to project this diagram onto here. And similarly to 3 ones, we have a quadruple which form a homological diamond. So occupy to 4 and 4 here. So the next is 0 and 6. And also this node which has 0 here. So now we can start putting decorations. So let's pick up the ordering of nodes as we had here. So let's say that this is x1, this is x2, x3, x4, and x5. So now we can draw them x1 here, x2 here, x3, x4, and x5. And now we can also draw them in the second color. So now it is x1 square, x2 square, x3 square, x4 square, and x5 square. Now following the same rule, now we can draw all these boxes like drawing here, here, and here. So we can deduce that there are some generators positioned in this way. So here would be x2, x2, x3, also this pair, x2, x4, x4, x5, and x2, x3, x5. And similarly, between the zeros generator, we can also draw in principle like that. Then it would be allocated pairs here, pairs there. Drawing here. Okay, let me see. So here, this should be located this way. This would be x1, x5. x1, x4. x1, x3, and likewise here we have x1, x2. Yes, but now this essentially all these generators they are not involved in the permutation, so they are not they do not generate equivalence between these two quivers. But in order to see this equivalence, we really need to see on the generators aligned between x1, x2, and x5, and generators aligned between x3 and x4 here. So now if I may erase like this unnecessary data, yeah, also we don't need this middle generator here. Now you want to put generators between this quadruple. And indeed now there is some non-trivial assignment to be made. So namely, yeah, so so there was, I think somehow drawing is not very nice. Maybe I need to remove this. So one pair must be arranged here, and the second pair must be arranged here. But we don't know, in principle, which one is which. And in fact, we have both possibilities at once. Well, not at once, but of course, like separately. So one possibility is to have x3 and x4 here. But then, of course, this pair must be x2, x5. So we don't have other options for them. Or we can have this permutation, and then we put like the second option is having x2, x4 here, and x3, x4, sorry, x2, x5, so x5 and x3, x4 here. So you see that, so the permutation that has been involved to generate this two equivalent quivers essentially can be traced back at the non-uniqueness of a map from the set of S2 generators to the set of monomials xi, xj. So essentially, this monomials xi, xj, you can also think of the value of Cij. And this is why there was some transposition between C25 and C34, which lead to, so this led to two equivalent quivers. We have like C decorate like one permutation and C another permutation. So this is very roughly how this permutahedron is explained at the level of homologies. And now, so since we had this data for quivers, so we can also play around and see if, so how this theory with unlinking could be realized in this example. And yes, so in order to do so, in fact, I need to do some extra probably definitions. Yeah, so let me try to write. So now we want, yeah, so just summing up that we have, there are two quivers with matrices C12 and C21. And well, what you can also see that if you just lift it all the way up, so since essentially, like you see that there is some thing which we call the moving unit. So there is some +1 which moves between these permutations. So then one can unlink one quiver, unlink second quiver, and end up with the same quiver essentially. So we can do unlinking here and to obtain a quiver which we call a universal quiver. So universal meaning that it contains, so by undoing unlinking, one can obtain the whole set of equivalent quivers, well, which is of course generated by this unlinking. So here we have this permutation. So permutation graph sits on the bottom of this structure. Yeah. So now let me introduce some other components which we call splitting. And what do we mean by splitting is, so again, I will give you a definition by an example. So first we want 0,1 splitting. So this is some operation which is labeled by pair of integers k and l, and we apply to quivers to obtain essentially q identities. And So we say the splitting operation is applied to a prequiver, and having a prequiver, for example, R, it maps a prequiver to a proper quiver, but you will see in a moment what it means. So here we have R plus 1, so this just shifts by 1. And what do we mean by this prequiver? The splitting is just the Q identity that I will write explicitly here below. So on one side we have the summation d1, d2. So it is very similar to the form of the quiver generating series, but slightly modified. Yes, in fact, I could have written here immediately. Maybe just better to give the general definition. So KNL, let's just put KNL here. So here we have R, and here there's some shift R plus K and R plus L. Because here I also write R and 2L plus 1. So far, this applies in general case, so we don't speak about nodes here, but in a moment, I will show you how this works. An example of node invariance. So on one side, we have a generating function, which corresponds to this quiver. This is generating function of the quiver C. And on the right-hand side, we want to put this C check, which we call a prequiver. And this is essentially just slightly different way to rewrite the generating series. So we have only one variable of summation, which corresponds to this value C ij equals to R. And here would be minus Q for R d check. Where the check. So this part is the same as we had in definition of if you had like this P of R, so this usual Quiver series. But then we multiply this by some additional factor, which looks like this. We have Q1 plus 2L D1 check x2 divided by x1 Q square D1 check times x on the check. So we have that, and note that so we have x1 here and here, but x2 enters only via this additional factor. And so overall, we just can rewrite the motivity generating function of some quiver whose adjacency matrix obeys some symmetry, and the symmetry in this case is given by this shift. So we have some R, and here we have some shift K and L. Then we can rewrite it in this form. And we can do so if you look all the way back at node homologies. So for example, we can also try to play even with trefoil. We have some non-trivial identities here. So for example, if you recall that, yes, so for the trefoil, we had this matrix C, which had 0, 2, 3, and 2 here. So one can indeed note that there are two prequivers. So one can write so one prequiver and another prequiver. So one would be 0, 2, 1, 1. So essentially a subquiver here. And the second would be having different pair of nodes, so 0 and 3, 1, 1. Just a different prequiver, a different subquivers here. And one can similarly write a Q identity of this form, which relates a prequiver to a proper quiver. So you see that if you think about it diagrammatically, so what happens is that we have a pair of generators in a homological diagram, and let's say that this pair of generators, they're related by differential. And by doing these algebraic manipulations with Cupac hammers, we mean that we apply differential and well, okay, not quite. Maybe one cannot say that we apply these differentials, but we follow a map which is aligned with the same way as the differential does. And we want to create like additional generators starting from a smaller number of generators. So for the trefoil, for example, if you have, so know that each of the prequivers has only 2 nodes, so we need to generate 1 node, which means that, like, using this language that we have to split 1 generator into 2. And indeed, if you start like with the nodes which are on the bottom, for example, so if you start with 0 and 2, and if you take this C check, which has the 0 and 2, so then the goal is to follow the path of a differential and to split. Essentially, we have like 2 possibilities. So we can split 2 into 3. Here we have splitting. Or we can do here, we can try 1 into 3. So this is also a different type of splitting. So in one case, if you split 2 to 3, so then this follows a path of 0, 1 splitting. And if it follows the path from 0 to 3, so then this is 1, 3 splitting. And yes, in fact, both of this 0, 1 and 1, 3, they correspond to the same prequiver. So since we have really started with these 2 bottom generators, but this prequiver is acting a bit different way. So we start with 0 and 3, and we need to generate 2. And in principle, we can also do it like in many ways. So we can act by 3, we can act by inverse of the splitting and generate 2 here, or we can, instead of having that, we can have like from 0, we can act by yet another operator and obtain these 2 here. But for us, probably, okay, this second scenario is not very essential, so maybe this is what we want more like to see. Because these splittings, they're aligned with differentials. And we can use this knowledge now. So yeah, just going back to figure 8 again. So let me see. So let's go back to homological diagram of figure 8, and you can see that there are some generators which could be aligned by differentials. And let's see how many types of splittings in principle we have here. So we can do, for example, so let's try 0, 1 splitting. So what it means? It means that we must start with this pair of generators. Let's draw them here. And we have this generator which is not being splitted, so we call it like a spectator node. And now we want to yes, homological degree is -2, 1, and 0. So now we want to split -2. We want to split it and we want to obtain -1 here, and we want to split -1 and to obtain 2 here. So we can also write, so you can just check that everything is consistent. So we can write pre-Quivers, you check. In this scenario, when we want to split -2 and 1, so the quiver would be of size 3. So this is just a subquiver in the Aether quivers that we have. Just for completeness, let me also write the generating variables for pre-quiver. Here we have A -2 Q where T -2x Q Tx. Oh, possibly if notation is kept correctly, then T must goes to -T here. All right, so now yeah, so now going back to permutohedron again. So what is a different way to see this permutohedron? So since we try to reproduce like all these quivers, basically starting from some pre-quivers, we can write some form of a diagram, and now this diagram would be that we start with this pre-quiver. So now we apply splitting, and then we obtain the 2 quivers that we had here, C12 and C21. And how to realize so why these 2 different arrows? So essentially, so here we split first -2, so then 1, and here we solve them. So here we split first 1 and then -2. And the results do not quite commute. And again, we have this permutohedral structure by permutation of the operations that we applied. So do we split first 1 or do we split first -2? So then this generates essentially the same permutation. And this generates these 2 equivalences that we have here. But since we spoke a lot about unlinking before, and we said that general permutohedral graphs are obtained from unlinking, so the main result is that we can model splitting by unlinking, and we can effectively redraw this diagram as a diagram of unlinking. So let me now draw this new diagram of splitting by unlinking. And this new diagram would be nothing but the hexagon relation for unlinking that we had on the previous lecture. So if you recall that for an arbitrary quiver, if you apply unlinking at ij and jk, so then this commutes in the following fashion. So here we have applied to jk, here we have to apply ij, and here we have to apply I, j, and k. And likewise here we apply I, j, k. So this holds universally for any Quiver Q. But now in particular, we want to put some familiar data here. So we want to put here Quivers for figure 8. So here we have C12, so here we have C21. And the question is, what's on the bottom here? And on the bottom would be the Quiver. So what's here? So you can take C check, and yeah, let me just redraw that. So it was 0, -2, -1. -1, 0, -1. And now we want to add one additional generator. And this generator essentially responsible for splitting and its values. So this generator does not correspond to any generator in node homology, but this will be just some auxiliary data that we put. And this generator must be chosen such that it models homological shifts when we perform unlinkings. And in this case, this generator is as following. So here we have 0, and here we have 1. And this value is 0. We can highlight this matrix. So this is what we had at pre-Quiver. And now this extra generator. And now what this extra generator does is that we can now hit by unlinking here. So essentially 2 times. So we can apply U so 1, 4 for this Quiver. Oh, sorry, 2, 4. And here we can hit by an operator U 3, 4, just to remove these elements. And so what will happen is you will see that by this augmented Quivers, which we call C prime check, so check because of this additional row and column. So then you can just put this C check prime on the bottom. And yeah, what is left is just apply here 1, 2, or 2, 4, 3, 4. Here you apply 3, 4, 2, 4. And you end up with exact, so following the hexagon relation for unlinking, in 2 steps, you will obtain 2 Quivers, which are actually bigger than Quivers for figure 8. But the structure of this additional node is very simple. So if you take yes, for example, so what is Q12 prime is just the same as Q212 union just a disjointed generator. And the same holds for U21. So this is the same as Q21. So one of the Quivers for figure 8 node, union also disjointed generator. And so recall that also last time I said that we can in principle remove generators that we don't want to have. And if you remove generators, we need to remove them carefully such that the upper structure is not altered. And we want to keep this structure which sits on top, but we want completely to discard the structure on the bottom. So here we want to essentially remove. So to obtain Quivers of figure 8, we need to remove this auxiliary generator which we have inserted here. So from here we can obtain, yes, we can just erase this, and then this gives us the two quivers of figure 8, and the surviving part of this diagram is only the top part. And we have, again, the same diagrams. Here we have C1, 2, here is C2, 1. And here we have universal quiver on top. Yes, so now, so in principle, the meaning of these pre-quivers and universal quivers in general is a little bit mysterious. So maybe if you have some ideas, so feel free to share. So this is very interesting, and so we don't know in general how to interpret these operations in terms of homologies. So it seems like there is some like algebraic manipulation with quivers, and we allow for this. So when the quiver matrix has certain symmetries, so then we can play around with this symmetry and, for example, to reduce information or to obtain like from some set of equivalent quivers, we can even obtain one universal quiver. Essentially, we also prove it as a theorem in general, so that every perimeter graph has a universal quiver. So Piotr, just a question: do I still have some time? Because I don't remember.
Yeah, we don't have anything immediately after that. So if you need, yeah, you can use some more time to finish.
Yeah, maybe I don't know. I thought about just showing one more example, or maybe just think for a moment. Yeah, maybe I give you this example as an exercise. So, so the next example, because I said we want nodes to up to 5 crossings. So, but we have 5.1 and 5.2 nodes. But 5.2 is a little bit maybe too complicated to handle. But 5.1 is a very nice example because its permutahedron has the following structure. So we have, in fact, for 5.1, we have 3 equivalent quivers. And there are 2 permutations. And these equivalent quivers, they could be completed into such a tower diagram. So we can unlink, first we can unlink pairwise quivers which are connected by permutation. And secondly, we can now unlink these 2 guys once more to obtain the universal quiver. So in both examples of 4.1 and 5.1, this universal quiver is unique. It is very interesting to understand like the relation. So interpretation of this universal quiver in terms of homology. So because this quiver is larger than the size of second color homology, but it doesn't have this redundancy of a permutation pair. And for 5.1, maybe just also draw the homological diagram. So it's the same as 3.1 because it has a subquiver, but it also has this additional pair. So this is the diagram for 5.1, and you see that there are so one quadruple essentially is this quadruple that we can permute, and so the second one is this one. So this is how you can see like the structure of this permutahedra graph. So permutahedra graph would mean that there is one component by 2 and also this component by 2. So there are permutations. Yeah, but now so it is quite easy to see how they unlink to the same quiver, but it is not so immediate to see like what's on the bottom of the structure. So however, yeah, one can show, so maybe I can just share the screen again and show you the picture for 5.1. Yeah, so this is the resulting diagram, and it is much more complicated than for 4.1. And so there are three quivers, C1 double prime, C12 double prime, and C2 double prime. So these are three quivers which correspond to conflict PT for 5.1, but only after removal of all additional generators. So in this case, we need to remove two generators, not just one. So since we start with some quiver on the bottom, and every arrow here is just some operation of unlinking. And you see that now we use heavily the properties of unlinking. So we use this hexagon and square identities. So this picture is basically tiled with the square and hexagons. And after a successive unlinkings, we can obtain this pentaedron, and we can also unlink it several times more to obtain a universal quiver on top. And the structure gets much more complicated if you look, for example, at next case. Yes, so going from 5.1 to 5.2 is much more involved, because maybe I can just draw it. For 5.2, the homological diagram is of this type. And you can already see that there is much more things going on here in comparison to this diagram above. So in particular, you can even estimate like the size of pentaedra for this quiver. So you see that there are several possibilities for permutation. So one permutation could be involved this quadruple of generators. So then there is also permutation in different colors by this quadruple. Also we have like this quadruple. Well, in principle, we can also have this quadruple and this quadruple. So there are much more possibilities for permutation. Yeah, but so we can show that the pentaedron uh, 5.2 consists of three copies of pi3, pentaedron of three elements. And all the story, like I said, with unlinking could be also modeled for this example. So one can also find universal quivers and prequivers and try to obtain this pentaedra by iteration of unlinking operations. So apart from unlinking, there is also a companion of operation of linking. And yeah, maybe just to finish that. So we have this UIJ, but we don't know if there are many more operations of this type. So namely, we want operations that preserve motivic generating series. So we have P of Q equals to P of some F of Q. And we know that, okay, so we have unlinking, but we also can define operation of linking, which instead of removing a pair of arrows, it adds a pair of arrows. But then it also adds a pair of arrows, like for these nodes in some way. I don't remember here, but yeah, but somehow this unlinking and linking operation, they're almost dual to each other. So if you apply unlinking at ij and linking at ij, So this is almost the same as Q, but you have to add a pair of redundant generators. And by these redundant generators, you mean that so the partition function of Q is equal to partition function of Q union this redundant pair. So it does not alter the partition function itself, but this is some sort of an equivalence, but not an exact identity between queries themselves. But we don't know, like apart from these separations, if there are more and how, like in general, these classes of all possible queries are organized. Yes, maybe at this moment I will stop and go to some question part if you have some questions.
Okay, thank you. Yeah. Are there any questions?
Can you flash some references?
Mm-hmm.
References, maybe?
Yeah. So I can, so maybe I can send them by email, or how would you prefer? Or you'd like, no, maybe it's better if I give it here, right? All right, so maybe let's, because I completely forgot about all this. So let me do this follows. So let's just recap. So we had lecture 1 was about like your series in general. Then the lecture 2, 3. Yeah, so this was about queue representations. Oh, you don't see the screen, right? So I do not share the screen. Right, so let me share screen. So now can you see all the screen right now?
Yeah.
Yeah, so this is the main reference for unlinking. So that we have this in last paper with Piotr, Elder and Piotr. So we studied this classes in general. So this is where we have this hexagon relations, splitting and pyramidahedra graphs from unlinking. This is general story. So then we have just tracing back, we have pyramidahedra for nodes and quivers. So this story relates to various nodes. Basically, the examples that you showed like lastly, but this does not say much about unlinking. So this is only about particular equivalences which arise from node homologies. Right. So what was there? Yeah, maybe I need to think about if you want to reference about query representations, I could maybe say them a bit later. So I just don't quite remember by heart. Yeah, but there is not much like literature about this topic anyway. I mean, that's
Okay.
about this main subjects.
Okay, are there any other questions? Okay, so let's thank Dima for the whole series. Please unmute yourself for clapping.
Thanks a lot.
Yeah, thank you very much.
Hope you
I'll
enjoyed
stop
that.
the recording.